Hey, good morning, ladies and gentlemen. I hope you guys are all doing well today. So, what we're going to be looking at today is all about lenses and how cool they are, and how to draw ray diagrams with lenses, and how to do our lens calculations. To go along with this video, I've also included on Google Classroom a series of links to other Khan Academy videos. So, I know this is a really tricky subject, a really tricky topic. So to supplement this lesson, you've got some other ones there that are also really good as well. So check those out, and hopefully that will help put everything together with lenses. All right, so ladies and gentlemen, for an object to be considered a lens, it has to be transparent, so light can go through it. And it has to have an index of refraction higher than air. So that means light is going to bend when it goes through there. Okay. Now, all lenses, ladies and gentlemen, they're broken into two groups depending on whether they focus light at a point. So a converging lens does that, or if they're going to spread out the light or scatter it a bit. So that's our diverging. Now, with a converging lens, their shape is thinner at the top than it is in the middle. So thinner top, larger in the middle. And this is also sometimes called a convex lens because that's pointing outward shape is convex. Now, our diverging lens, the top is going to be thicker than the middle. And that is also called a concave lens, as we have that cave shape to the lens there. Okay. So now that we've got our two type of lenses defined, we are going to look at a couple of key terms we need before we can begin our math and our ray diagrams. So the first couple of things we're going to look at is our principal axis and our principal plane. So when we're going to be making ray diagrams, we need to have a couple of reference points here. So the principal axis is going to be an imaginary line that is perpendicular to the lens and cuts the length of a lens in half. So that is this guy here. Okay, so that's a very useful piece that we're going to be using. We're going to be assuming that for our purposes, all of the objects we're going to be looking at through our lenses are going to be sitting on this thing, and our focal points are also going to be on that as well. And then our next piece, our principal plane, it's perpendicular to the principal axis, and it runs lengthwise through the middle of the lens, and it chops the lens right in half. So that's this guy here, this line right there is our principal plane. Okay, these dots here are your focal points, and we draw these on both sides of the lens, and they're defined as the point where all parallel light rays are going to meet after they go through a lens. So we'll talk more about that in a bit when we're drawing our ray diagrams. And of course, our optical center, just like it sounds, is right in the very middle of that lens. So our optical center is that dot right there. Okay, so spend some time becoming comfortable with those terms, and then we're ready to go on to the next part. Okay, so we're going to scroll down, and we'll talk a little bit about image type and the size orientation that you can get with a lens when you're going to be looking at an object through it. Okay, so for size, so with like a magnifying lens, you can have a lens that's going to make the image look larger, and sometimes images or lenses will be designed to make the images look smaller. Okay, so smaller or larger, or on occasion you can have an object that is going to look this to be the same size when you look at it through a lens. Now, as well with a lens, sometimes you can have images that are going to be upright, and sometimes you can have an inverted or upside down image. Um, what's really sad here with that, we don't actually have class. I can't pull out the box of lenses, and we can't play with laser beams and lenses, so which is quite upsetting actually. Okay, so those are the two types of images. They can be upright or they can be inverted. And then we also have two different types of images. So we have virtual images or real images. Now, one of the Khan Academy videos does a really, really good job of explaining the difference between inverted and real images. And I think that's the first video on the list to go with this one in Google Classroom. So have a look at that. And it did a really, really good job of explaining the difference if this brief explanation doesn't quite make sense for you. So a real image, it can be projected onto a screen because it's on the opposite side of a lens in comparison to an object. Whereas virtual image, you can see them, but you can't put it onto a screen because it's on the same side as an object. So the most common type of virtual image that you will deal with is your own reflection. So if you are going to be looking at your image in a mirror, the image that you are seeing is on the same side of the mirror. And because it's on the same side, you can't project it onto a screen. So if here is a mirror and here is you with your beautiful face, and well, back behind here, you've got a wall. You don't actually have an image on this side. It looks to you like you have an image back there, but you don't. Your actual image is going to be on the same side that you are. Okay, so that's with a mirror and virtual images. With a lens and a virtual image, here is your lens. If here is your object, arrows are often used as objects. If you happen to have an image that's on this side, for example, and if that's your image, then that's going to be a virtual image. And if you have an image of this object here, that's going to be a real image because you can project that one onto a screen. Okay, so have a look at that Khan Academy video. Might be a good time to pause this one, go watch that one, which is all about your virtual versus real images. Okay. All right, so ladies and gentlemen, we're going to be looking at the rules for drawing ray diagrams. So we've got this simplified down into 3 rules. That's 4. 3 rules for you guys. Okay, so ladies and gentlemen, any image that you're going to be seeing through a lens is going to be created where all of the beams of light have refracted and met. That's the key piece, where all of the rays of light are going to meet after they pass through a lens. Now remember, sometimes the rays are going to meet on one side of a lens, sometimes they're going to meet on the other. All right, so now, ladies and gentlemen, if we did have exams and diplomas, I would be telling you guys to memorize these 3 rules, but we don't have exams, we don't have tests, so don't worry about memorizing them. Maybe put a little sticky in your notes, so that way when you get to these questions on your assignment, then you can look at these ones. Okay, rule number 1, numero uno. Any ray or beam of light that's going to pass through a focal point of the lens is going to refract parallel to the principal axis. Now, this one only applies to a converging lens. It does not apply to a diverging lens. Okay, so here is our converging lens here. The arrow is your object. Okay, so here's the object, and we're going to take the beam of light, which we're always, just for the sake of ease, always have this light, have the ray of light we're going to be dealing with starting from the top of that object. It's going to be a lot easier because really the whole object is going to be either reflecting light itself or emitting light all over it. So it's just so much easier to keep track of one point at a time. Okay, so we're going to start here. I'm going to switch colors off of red so it's a bit easier to see. So we're going to start at the very top of our arrow, and our light, now for this, please use a ruler. I can't really easily use rulers with this writing pad, so I highly recommend you guys use a ruler with this. Okay. So you're going to start at the top and you're going to draw your ray of light going right through that focal point. Now, because we went through the focal point, once it goes through that lens, it's going to refract so that way it is parallel. So to this guy, principal axis. So here is your line. Notice it's parallel to the principal axis. The ray of light went from the tip of this object and it went through the focal point, will then refract to go this way. Okay. So, and once again, it does not apply to a diverging lens. It only applies to a converging lens. Okay, now remember that these beams of light are this object is going to be reflecting beams of light from all over it. So that means that's not going to be the only ray of light we're dealing with. And if we had only one ray of light, well, we wouldn't really be seeing the images properly. So let's go look at some of the other rays of light that are going to be coming off this object. Rule number 2. Any ray of light that is going to be parallel to the principal axis initially is going to refract, so it passes through the focal point on the other side of the lens. Okay, so for a concave or a divergent lens, when you have this rule, it's going to scatter the light away. So that means we're going to have to extend that diverging ray back onto the opposite side of that lens. So I'll show you how that works on our next picture here. So here we have our converging lens, ladies and gentlemen. Now I'm going to switch back to the blue. So this is the beam of light, the ray of light that we've already looked at. So this ray of light is starting parallel to that principal axis. So here's your principal axis. Okay. And with that beautiful principal axis, ladies and gentlemen, as it's going to hit that lens, and as it goes through this lens, it is going to refract, and then it's going to go through the focal point. Remember, we have 2 focal points. It's going to go through this one on that opposite side. Now, it's going to keep going, and you're going to make a straight line because you're going to use your rulers. And we're going to wind up with a really, really nice line there. And notice here, ladies and gentlemen, that the 2 rays of light converge, the 2 rays of light meet. So because we had our rays starting from the top of this image, that means that this is going to be where the top of our image is actually going to be. The rays come from the top of the object, and where they converge is going to be the top of the image. So this here is our object, and we tend to use arrows to infer what our object is, and that is going to be our image. Okay, so we're also going to make a note here. Top image is where the rays meet. Okay. So, ladies and gentlemen, that's rule number 2, looking at a convergent lens. We're now going to look at rule number 2 on a divergent lens. Okay. Now, on a divergent lens, remember that the beam of light is going to scatter away, okay, from the focal point, scatter away from everything else, scatter the light. So we're starting at the top of that object again, and then we start running along this way until we hit the lens. Now, this is not going to bend down like this. This is the divergent lens. The rays of light bend away from each other. So you're going to take your rulers, and where that ray is, you're going to measure backwards, okay, through that focal point. Okay, so what this is indicating to us is that we're most likely going to be ending up with an image on this side. We're going to wind up with a virtual image here. This ray of light, the ray of light is actually going to be going that way. Okay, so that's how we're going to draw this one. Okay, so the beam of light goes out that way, and then we can extend our ray this way. Okay, all right. So, ladies and gentlemen, that's your diverging lens. And now we are going to look at rule number 3. Now, rule number 3 also applies to both of them. Any ray that passes through the optical center, so remember the optical center is that very, very middle point of the lens, it will pass through without any refraction. Both types of lenses, this is going to be the case. So I'm going to switch back to blue. On this diagram, we've already drawn these 2 rays. And now we're going to be looking at the third. We're still starting from the top of our object, and using your rulers, you're going to have that ray of light pass through that optical center. And it's going to continue, keep running, keep using your rulers, and it's going to continue this way. Notice it still is going to converge at that same point where our other rays did, which is telling us that that's also fits with getting our image to be showing up right there. Okay, so that is with your converging lenses. With our diverging lenses, the rule's the same. We are still starting with the top of our object. The ray of light is going to pass through the very center. There is going to be no refraction of that object. Well, now notice the dotted line from our previous ray that met up with the focal point is now meeting here. So this image is smaller. It's virtual because it's on the same side as the object, and you can't project that onto a screen. And it is upright. Whereas this image is larger. Okay, it is going to be a real image because it's on the opposite side of the actual object. Okay, so you could project it onto a screen, and it is an inverted, so upside down image. You want to know something really cool? We're going to pause for a moment and we're going to talk a wee bit about biology. So do you guys remember when dissecting eyeballs in Bio 30? I really hope you guys all got the chance to do that. You will have noticed that the lenses in your eyes are converging lenses. So the image that is projected onto the back of your retina is actually upside down. Our brain flips it right side up. And what lobe of the brain processes visual images? Occipital lobe. You got it. Right at the back right there. So ladies and gentlemen, there's your biology application to what you're doing. So anyone who does any type of optical medicine will be very familiar with these principles as well. So that is your bio moment. Okay. So, ladies and gentlemen, okay. So what we're also going to do with this point is we're going to look at another example. We're going to draw some ray diagrams. I want you guys to use your rulers, please. I am going to attempt to make my lines as straight as possible, but it's a pain in the butt to try and use a ruler on the fancy writing tablet that I've borrowed from Mr. McLeod. Okay, so here is our object. Here are our focal points. And now we're going to try and determine what our image is going to look like. Now, notice with our previous objects, they were all behind the focal point. This is now an object that is in front of the focal point. So my rules are still going to apply. So I'm going to start by drawing a ray of light that's going to go parallel to this principal axis here. So now I am going, once it's parallel, it's going to refract, very nice, through the focal point. Your guys' diagrams are going to look a lot nicer than mine because you have the ability to use rulers. And then I am going to have another line that's going to go through the center. Now, I can't have a line go through the focal point here because my focal point's behind the object. So I can't use rule number 1. I have to use rules 2 and 3. So now I'm going to have my beam of light go through the center unrefracted. Well, notice what we have now. I have no image on this side. Why do I have no image on this side? Because the rays don't converge, absolutely. However, like with my other divergent lenses, when we don't have our rays meeting, we can extend them back. So I'm going to extend this guy back like that, using your rulers. So yours is therefore going to be nicer than mine. Well, oh, look at this, guys. They have converged. The rays of light have converged back here. Okay? So that means my image is actually going to be, we'll use green because why not? My image is going to be back here. Okay? So now let's look at my image. My image is imaginary, virtual, because it's on the same side as the object. It is going to be larger than the object, and it is going to be upright. All right. So ladies and gentlemen, we've got some practice problems down here. Don't do any dimensions charts. And when they say a positive lens, they mean a converging lens. So watch out for that. As well, this would also be a good time to pause this video and then go and watch some of the other Khan Academy videos. I've got a whole bunch of them on there that are all about converging lenses and diverging lenses, what they tend to call convex and concave lenses, and ray diagrams, and they just do a bunch of them. And it is going to be really, really helpful for you guys to watch a bunch of those videos. So pause the video here and go watch some of the ray diagram videos for Khan Academy, and then come back so we can look at our equations. All right. So, ladies and gentlemen, I'm going to assume that you guys have gone and watched those ray diagram videos and done some practice problems. And we're now going to do our next video here on our equations for lenses. Okay. And I'm hearing some clicking of puppy toenails. It looks like Freya's coming to say hi. You coming to say hi, Freya? Yes, you're a good girl. Yeah, she's a good girl. Okay. So ladies and gentlemen, on your data sheets, you will find these two lovely equations here, and these are what are called your thin lens equations. So these are going to work for very, very thin lenses. They're not going to be working for a lens that's going to be like this large or what have you, because we're going to be having a whole bunch of other diffraction, more diffraction happening inside the lens itself. So these are your thin lens equations. So ladies and gentlemen, with our thin lens equations, you can use any units so long as you're consistent. Okay, meters, centimeters, what have you. Okay, so ladies and gentlemen, we're going to go through each of these here. Now, once again, with this one, pick any of the 3 pieces you need. So any 2 halves you need. So you could pick magnification is equal to the height of the image over the height of the object. You can have height of image over height of object equals the negative distance of the image over the distance of the object, or m is equal to negative di over do. So pick any 2 bits that you need. You don't have to use all of it. This one, you need to use all of it. All right, so di is the distance of the image from the principal plane of the lens. And DO is the distance of the object from the principal plane of the lens. And DF is the focal length or point, so the distance of the focal point from the optical center. HI is the height of the image. HO is the height of the object. And M is the magnification, which is a unitless number. Now, if your magnification or M value is larger than 1, It means, ladies and gentlemen, an absolute value of 1, it's going to be an enlarged image. So, or if it's smaller than 1, it is going to be a reduced image. So if we were going to be having tests and diploma exams and what have you this year, I would be saying, memorize this. But we don't have exams, we don't have diplomas, we don't have the things, so you don't have to memorize this. But what I would also do is I would put a sticky beside this page in your notes and with a big star on it, so that way you have this. Or heck, you can print off this page and staple it to your data sheet, so that way you always have it, because you're going to need it for all of your lens equations. Okay, so I'm going to put a big star here, and I'm going to write memorize here because I just can't help myself. Okay, now whether they're going to be, these numbers are going to be positive or negative, is going to mean something different. DO, so the distance of the object, is always positive. DI, positive for real images, okay? Negative for virtual images. F, positive for converging, negative for diverging. The height of the image is positive for upright, negative for inverted. Height of the object, always positive. And M, positive for upright, negative for inverted. Okay, so it's a lot of stuff. Memorize it if we have diplomas, which we don't, or print this page off and like staple it to your data booklet so you always have it. Okay, so what I'm also going to do with all of this is underneath this, I'm going to draw a bit of a diagram for you. So once again, it's me drawing, so bear with me. So just to kind of label what all of these different pieces are. So here is your lens. Okay, it's supposed to be an actual nice lens. Please bear with me here. Okay, so we have our principal axis and our principal plane drawn. And I'm going to label this as F. Okay. And then I am going to take blue and I'm going to label all these values. So this F, our focal point, our focal distance, is from there to there. From there to there, it's going to be the same number. And now I'm going to take my object here and I am going to draw my image here. So that's my image. So this value here is object. That's the height of the object. Okay. And this from here to here is the distance of the object. I'm going to switch colors here. I'm going to go to pink and I'm going to, let's pretend my image is over here. So this here, this value here, excuse me, the dog is being loud. You're being noisy. Can you give me 1 minute, please, Freya? Okay, 1 minute. This is the distance of the image and this is the height of the image. Okay, so ladies and gentlemen, I hope that helps. I'm just going to need to pause the video for now right here before we go to our calculations so I can let my dog out. So I will be right back. Okay, please bear with me here. I first actually pause this thing. Okay, I'll be back. Okay, we are recording now, ladies and gentlemen. We're back. I've let the dog out. She's no longer barking and whining at me. Okay, so now that we have your lovely diagram here, so I hope that helps with what all the letters and notations mean, we are going to scroll down and we are going to look at our calculation examples. Okay, so ladies and gentlemen, the reason why I want you guys to have your table above right in front of you while we're doing all these calculations for lenses is going to become apparent pretty quickly. So a converging lens has a focal length of 0.22 meters. Okay, we're going to pause here. Ladies and gentlemen, converging lens, that means right away our F is going to be positive. And our focal length is going to be 0.22. So my F is positive 0.22 meters. Okay. And once again, watch your units. They have to be consistent. If an object is placed 0.41 meters in front of the lens, okay, it is going to be the distance of the object. And ladies and gentlemen, the distance of the object is always positive. Okay. And identify the characteristics of the image that it will be produced. Okay, so we want to see, is it going to be larger or smaller or real or virtual or upright or inverted? So we got to figure out three things about it. Okay, so we have F and we have our DO. Well, looking at your data sheets, you have your equation of 1 over F is equal to 1 over DI plus 1 over DO. Okay, so now, ladies and gentlemen, we're just going to rearrange this guy. So we're going to get 1 over DI is going to equal 1 over F and then minus 1 over DO. Okay, so I'm now going to put my numbers into my equation. All right, so 1 over, so I take my value of F, which is positive 0.22, and I'm going to subtract that from my positive 0.41. It is not a bad idea to be writing in these positive values because the positives and negatives actually mean something here. So it's a good idea to help keep it straight so that way you know which value is which. So when you throw that number into your calculator, this is the common piece to watch for. Don't make a mistake with how you write this. When you put this number in your calculator, that is not DI. That is 1 over DI, okay? Because we can't miraculously move DI to the top of that dividing line. We have to do something to get it there. And what we do to one side, we have to do to the other. Okay, so when you put this into your calculator, you're going to get 2.106 ... These guys are on the bottom. Their units are meters. This guy's units are meters to the power of -1. Or 1 over meters. It's on the bottom of that dividing line. This guy's on the bottom of the dividing line. To get them both flipped, in your calculators, you are going to take the inverse. So you're going to push that power of -1 button. Okay? So you take the inverse of both sides. So on your calculators, you guys see this power -1 button right there. That button, ladies and gentlemen, is what you're going to hit as this last step here. Don't forget about this guy. Don't forget that last step. That's super, super important. Okay, so once you've put that into your calculator, you're going to get, with your SIGDIGs, your DI is going to be positive 0.47 meters. Okay, now I'm going to switch colors, and this value here is positive. Because the value is positive, ladies and gentlemen, when you look at go back and look at your tables, and when you see DI, positive means it's a real image. Excellent. Okay, so we know that the image is real. We know that the image is going to be on the opposite side of that lens and that we can project that onto a screen. Okay, so now I only have one of the three characteristics. I'm going to need to see, is it going to be larger? And I'm going to need to see if it is going to be upright or inverted. So when I look at my table, ladies and gentlemen, it's positive for upright with magnification, negative for inverted. Well, that can tell me if it's upright or inverted. And if I get a value larger than 1 with my magnification, well, guess what? I'm going to have a magnified image, a larger image. If I get M smaller, then I've got a smaller image. So I can calculate M and then get the remaining 2 pieces. So that's what I'm going to do. So my magnification equation is, I've got 2 different pieces. I've got the height of the objects and the distance of the objects and images. Well, I don't have the heights, so I'm going to use the distances because that's what I've got. So magnification is equal to negative DI over DO. So the negative distance of the image over the distance of the object. So guess what? I have both of those values. So I am just going to plunk my numbers in there. And now because of that, this negative here, it's the negative 0.47. And this negative is already in the equation. Okay, divided by 0.41. And with my appropriate significant digits, I have negative 1.2. Magnification, ladies and gentlemen, is unitless. I'm going to jump over to blue. Negative. When you look at your table, ladies and gentlemen, negative is going to tell you it is inverted. And according to your notes, the little blurb I had you guys star right above the table, whenever the value is greater than 1, the absolute value, ladies and gentlemen, is going to be greater than 1, it means it is going to be larger. So, ladies and gentlemen, we have a real inverted larger image with this particular lens. Woo-hoo. All right. So, ladies and gentlemen, question number 2. Number 2. Okay. So, this one, we are going to have a glowing object that is 4 centimeters tall is placed 2 centimeters in front of a lens. Okay, pause. Okay, do we have information helpful to us at this point? We do. So what we've got is the lovely number of HO. According to your tables, the height of the object is always positive. Okay, and is placed 2 centimeters in front of the lens. Well, that is our DO, ladies and gentlemen, and DO is always positive. So we have 2 values that are always positive. If the height of the inverted image, now, height of an inverted image, negative. So that means my H, not ow, where's my eraser? There we go. HI, ladies and gentlemen, is 9 centimeters. So because it's inverted, you have to have negative 9 centimeters. Okay, so ladies and gentlemen, we have then been asked to calculate the distance between the object and the image. So we are wanting to calculate, we're just going to call it D for distance. So what we are going to need to do before we can actually figure out the distance between the object and the image is we're going to need to figure out, well, where is this image? We're going to need to find out, is it on opposite sides of the lens? Is it on the same side? Are we going to adding? Are we subtracting? Like, what are we doing? So before we can figure that out, let's figure out what type of image we're dealing with and where it actually is. Okay. So what I am going to need to do to calculate how far between the object and the image is, I need to calculate my DI first. So that's the first thing I'm going to need to calculate. Well, I'm trying to find DI. I have the height of the image, the height of the object, and the distance of the object. Well, I've got my magnification equation that has 3 of the 4 of those. So I have my height of the image divided by the height of the object is equal to the negative DI divided by DO. Okay. So once again, that magnification equation, you only pick the 2 halves that you're going to need. So I'm going to rearrange this guy. I'm trying to find my DI, so I'm going to multiply by DO, and then I'm going to multiply each side by -1 to move that -1 over. So I'm going to wind up with DI is going to equal negative DO times HI divided by HO. Okay. So I'm going to plonk my numbers into my equation, ladies and gentlemen. That negative is going to stay on the outside. My DO, ladies and gentlemen, is going to be I lost my spot. I lost my spot, ladies and gentlemen. No, I didn't. We're fine. We're good. Okay, 2 centimeters times the height of my object, which is -9. And we're going to divide that by 4. Okay, so our 2 negatives here are going to cancel each other out. We're going to wind up with a positive, and we're going to have our DI as going to be 4.5 centimeters in your calculator. It's positive. Now, ladies and gentlemen, let's think back to our lovely table. A positive value here is going to mean positive for real. So, for real. Okay, so let's think about this for a moment. We know that a real image is on the opposite side of the lens in comparison to the image. So I'm going to do a quick rough drawing here. Now, once again, rough. All right, so here's the lens. It doesn't say what kind of lens it is. I'm just going to use wonky converging lens just for the sake of this. And I have my object, which is here. Now, we know that this guy here, my DO, is 2 centimeters. Okay, we know it's an inverted image, so the inverted image is going to be over here, so, and it's larger, so we're going to have a larger inverted image here. And I know that my DI is this value here, which is my 4.5. So when I look at this setup, the distance between the image and the object is the value of D that I'm trying to calculate. So that means this D that I want is going to be equal to my distance from the object to the center of the lens plus my DI, which is the distance from the center of the lens to the image. So I am going to take my 2 values of 2 centimeters plus my 4.5 centimeters, and I am going to wind up with the distance between the image and the object to be 6.5 centimeters. Okay, so as you guys can see with this, the calculations themselves aren't necessarily the most important part. You have to understand what the numbers mean, the significance behind those positives and negatives, and what it means with where these things are in relation to the lens when it comes to solving our problems. So that's going to be one of the trickiest parts with this particular set of calculations, is what these numbers mean. So normally I would just tell you to memorize that chart. We don't have exams, so keep that chart from the previous page in your notes on hand whenever you're doing these calculations, or just make a copy and staple it to your data sheet. I think I've said that like 6 times. So when I say things like 6 times in the middle of a lesson, what does it actually mean? It means it's important and it's something you should be doing. Yes. Okay. Ladies and gentlemen, last question, and then we're letting you go for Easter break. All right. So I am going to scroll down to our last question. And this, ladies and gentlemen, is one of your guys' absolute favorite types of questions. Math wizardry! Oh, yeah. Also known as substitution. This is where, if we were in class, you guys would all be groaning and complaining. And I would then probably make some joke about it. I do miss you guys. Okay, a diverging lens has a focal length of 20 centimeters. So we're going to jump back to red here. Okay, so ladies and gentlemen, diverging lens has a focal length of 20 meters. The fact that it is diverging, it means that F is going to be negative. Okay, where should the object be placed? So now when we say where, we're trying to find our DO in order for the virtual upright image. Okay, virtual upright image. Okay, virtual means that DI is going to be negative. Upright means that our magnification is going to be positive. Okay, and will be half as tall as the object. Okay, so half as tall as the object, that means my magnification is going to be positive 0.5. I've got an extra dot there. We're going to try and get rid of that. There we go. Okay, so our magnification is going to be 0.5. We also have another piece of information here that we could also use. Our height of the image is going to equal positive 1/2 of the height of the object. So that's what it could also mean. Now, I'm going to go with where m is going to be my 0.5. That's the route I'm going to choose to go with this. But if you're wanting to, you can go a whole different way about going about this by using that second option I just mentioned. And just for fun, you guys should give it a try. Okay, so ladies and gentlemen, we've got a whole bunch of substitutions to do. So we are trying to find our DO. Okay, so we have the focal point, and we have our 1 over f is going to equal 1 over DO plus 1 over DI. Well, we're trying to find DO here, but we don't have DI. However, ladies and gentlemen, what we do have is we have the magnification. I can get my DI in a different manner via substitution. So my DI, erase. Okay, my magnification is equal to negative DI divided by DO. Well, I am trying to find DO. So I'm going to keep that, and I want to get rid of this DI. If I have two DOs, which is what I'm trying to find, then I am going to be able to do some math wizardry in order to get it down to be one DO, which I will then be able to solve for. Okay, so I'm going to rearrange this to get my DI on its own so I can replace this. So when I rearrange this, my DI is going to equal my negative MDO. So what I can do is I can take, if DI is equal to negative MDO, I can take this DI and replace it with negative MDO. Well, I have M and I'm trying to find DO, so this is okay. All right, now I'm going to scroll down a bit so I don't have to write on my face. So 1 over F is now going to equal 1 over DO plus 1 over negative MDO. Okay, now, ladies and gentlemen, we're going to be adding fractions here. What is your rule when adding fractions? This is when in class I would hear lots of complaining about, I hate fractions. Too bad, guys. You have to use fractions here. No decimal is going to save you today. All fractions. So when we're adding fractions, you have to make sure that they have a lowest common denominator. So we have DO and negative MDO. Well, to make sure they have a common denominator, I'm going to multiply this side by negative M. So if I take my 1 over F is going to equal my negative M times 1 over DO plus my 1 over negative MDO. Now, when I multiply everything here all the way through, I'm going to have negative M over negative MDO. Now notice these two could technically cancel out into one. So I can still do this without actually changing the numeric value of anything. Math wizardry. Woo! That's why math is awesome. Okay. So now, ladies and gentlemen, I can add these together. Okay. So I'm gonna scroll down so I don't have to write on my face. So 1 over f. Now when I add fractions, the bottom fraction is going to stay the same. Okay. So negative m d o, okay, is that bottom, that stays the same. And then I add the numerators. So negative m plus 1. Okay. So now I just need to now look at this. I only have one DO now, which is what I want, which is what I'm trying to solve for. So I'm going to rearrange this guy, and I'm going to multiply both sides by f to make this nice and linear. So 1 on this side is going to equal my negative m plus 1 times f divided by negative m do. I'm going to multiply both sides by negative m do. Okay. Now I'm just going to jump up here to rewrite this guy here. So my negative m do is going to equal negative m plus 1 times f. And then, ladies and gentlemen, I'm going to divide by negative m. Now, you cannot cancel that out. They're being added. Okay, so don't cancel out negative m. So, ladies and gentlemen, do is going to equal negative m plus 1 times f divided by negative m. Okay, I'm going to plonk my numbers in my equation. So, ladies and gentlemen, negative 0.5. I'm going to scroll down so I'm not writing on my face. There we go. My negative 0.5, which is my negative m, plus 1, times my f, which is negative 20. And I am then going to divide this value by my negative m, which is 0.5. And I am going to finally get my DO of positive 20.0 centimeters. Okay, so that means the distance that I have to place this object 20 centimeters in front of the lens to get the desired image. Okay, so ladies and gentlemen, I hope you guys enjoyed that. We've got a bunch more practice problems for you guys to do. And we've also just got a reminder here at the bottom that convex lenses are converging, concave, or diverging. This is also going to be a really good point for you guys to go and watch the remaining Khan Academy videos, which is going to be about our thin lens equations. So I got some of those in there. I also got a cool video on a practical applications of lenses, which is a lovely camera lens video, which is put in there by Canon. So the end is a little bit of a ad about why Canon lenses are cool, but the video is even cooler. All right, so ladies and gentlemen, I hope you guys have a good Easter break, and I will see you guys when we get back. So, ladies and gentlemen, fires, injuries, or explosions. Have a good day.